Welcome back, everybody. So now we want to see an application on a combinatorics result of compactness for sentential logic. So we said compactness for sentential logic is kind of the simpler version, which we actually proved in the last video, but it's still quite useful in some situations if you find your way around. So sometimes, like the compactness for the other one, for first order logic, is more clear sometimes how to apply it. Well, usually it also requires tricks, but this one, you need to understand what you're doing. And if you do it the right way, you can get the corollaries from these results. Okay, so let's start with the definition of a partial ordering. So a partial ordering consists of a set of elements, a domain, a universe, like we call it V in this case, and a binary relation, where this binary relation satisfies three properties: transitivity, reflexivity, and antisymmetry. Okay, so these three properties that it needs to satisfy. What are these three properties? Transitivity is the most important one and says that when you have that x is below y and y is below z, then x is below z. Okay, you will expect that if you have ordering among things, right? The next one, reflexivity, it's a very simple one, and it just says that every element is below, less than or equal itself, just because, well, it's equal itself. And the last one, antisymmetry, says that for every x and y, if x is less than or equal to y and y is less than or equal to x, then x must be equal to y. Okay, so you cannot have things that are not equal being less than or equal and greater than or equal each other, right? So, okay, so those three things make a partial ordering. So, for instance, consider the set of letters A, B, C, D, all the letters of the alphabet. Okay, that's just A. And now consider this set. This is our universe. Now we want is a set of finite strings over those letters. Okay, so we saw that at the beginning. So this is less than or equal omega, means the set of all finite tuples taken from this set A. So in this case, a finite tuple is nothing more than just a sequence of a string of letters, right? So A, B, Z, N, A, D, that's a sequence of 6 letters, so that's a tuple of letters, so that's something that belongs to A less than or equal omega. So any string of letters will belong to that. And let's consider the following ordering. Given two strings sigma and tau, so these are a string of characters sigma and tau, let's say that sigma is an initial segment of tau. Let's say that sigma is strictly less than tau, even only if sigma is an initial segment of tau. So the word contains the other one. So for instance, the word ABZ is an initial segment of the word ABZNAD, right? So that's why we say that it's less than or equal. Okay, but there could be words, for instance, that don't contain each other and they're incomparable under this ordering. Some words are comparable, like if they extend each other. Some words are not, and then you get here an order that is transitive, reflexive, and antisymmetric. So that is a partial ordering. Okay, good. So a linear ordering is a partial ordering that also satisfies that whenever you have two elements, they must be comparable. Okay, so in the example before, we had there could be words that are incomparable to each other. But now, like whenever we have two elements, x and y, they have to be comparable. So they look like a line. That's why they are called linear orderings, right? So the ordering is all the elements are comparable to each other, so it looks like a line. So the examples that we know, there are a few ones that we have used so far. The reals with less than or equals, the integers with less than or equals. We saw the double chain of the integers plus the integers. So those are all linear orderings. Any two elements are comparable. If we take, for instance, the lexicographic ordering on the set of words, the set of strings of letters, this is the lexicographic ordering is the one used in the dictionary, then that one is a linear ordering, because even if one word doesn't contain the other, we decide how to order them, right? So the dictionary kind of is a linear ordering of all the strings of characters. So A less than omega. Okay, so in that case, any two things are comparable. Now let's consider the following notion, the notion of linearization, okay? So a linearization of a partial ordering is a way to kind of squish it to make it into a linear ordering, okay? So formally what we're doing is considering another ordering, triangle leg, which is compatible with this one, and so that it's linear, okay, on the same domain. So we have, by compatible, formally what we mean is that for every two elements P and Q in P, if P is less than or equal Q in the partial ordering P, then P is triangle leg less than or equal Q. Alright, so it preserves the ordering, but there are going to be things that are incomparable, so where this is not the case, but still this is the case. Okay, so there are many more things comparable here because we wanted to make it a linear ordering. So let me draw an example. Here is a partial ordering, so it has 6 elements, and I draw it so that the elements that are higher up are greater than or equal the ones that are below, right? So in here we have P1 is above P0, P2 is above P0, but P1 and P2 are incomparable in this here. And then P3 and P4 are also incomparable, but they are both above P1 and P2, P5 is on top of them. And if we wanted to linearize them, essentially we want to squish it to make it into a linear ordering. So that means we have to make a decision of who we want to be larger, P1 or P2, and then we have to do the same about P3 and P4 in a way that everything is compatible. So, for instance, this one here will be a linearization of the P. Right here, what we did, we decided to put P1 on top of P2, and we decided to put P3 on top of P4, right? So P3 is on top, P2 is on top, but then all the other relations are preserved, right? So P4 is higher than P2, here P4 is higher than P2, P4 is higher than P1, P4 is higher than P1. So all the relations that we had here are still preserved, but we put more relations to make it a linear ordering. We could have done it in a different way. This one up here will be a different linearization of the same partial ordering, but now putting P2 above P1 instead of P1 above P2. But they were incomparable before, so we could choose either of them. And okay, in this example, in this very simple example, it's very easy to say how to linearize. But if you have a more complicated partial ordering, this takes a bit more work. So there's a theorem that says, you can prove, that says that if you have a finite partial ordering, you can always linearize it. So you can always do this process of making it into a linear ordering by adding more relations to the things that were incomparable. When you have a finite linear ordering, this proof is not very hard. You just have to do it one step at a time, making sure you don't break anything, and the proof works fine. But what we want to prove today is that this is true for any partial ordering of any site. For every partial ordering has a linearization, okay? And we want to use compactness to derive this corollary from the theorem. We're not going to give a proof of the theorem, but we just want to see how the theorem implies this corollary. So from knowing something about finite partial ordering, we can deduce something about all partial orderings, okay, of all sizes. I mean, this corollary can be proved in different ways. You don't need to use compactness. There are other things that are other applications that are a bit more interesting mathematically, but this is a good example. So this is a good example of how to use compactness to prove something, okay? So every partial ordering has a linearization, and we want to use compactness for sentential logic. So let's get into the proof. So let's start with a partial ordering P as we had before. And now we want to prove that there exists a linearization for this partial. We want to prove that there exists a linearization triangle less than or equal of this ordering, okay? So it has to be something that is compatible with the ordering, but it also that it is a linear ordering, okay? So how are we gonna do this? For each pair P and Q from the set of vertices, we are going to consider a sentential variable symbol. Okay, so this is a variable symbol in sentential logic. It's representing a sentence. Remember, the variable symbols in sentential logic are representing predicates, are representing concepts. And we are going to consider one that we're going to call A sub PQ. Okay, so this is a variable in sentential logic. And when we look at this, what we're going to think of is that APQ is saying that P is less than or equal Q in this triangle extension that we want to define. Okay? So APQ is a variable symbol that could be either true or false depending on our truth assignment. That it's going to be, it represents P less than or equal to Q. Okay? What we want is a truth assignment V that takes, remember, a truth assignment maps each variable symbol APQ to an either true or a false in a way that if we define triangle less P triangle less Q if and only if the variable APQ is assigned true, then what we get is a linearization of less than. Okay, so we want to find, well, to prove that it exists a variable assignment, a truth assignment, that if we define triangle x this way, but saying what APQ means that P is less than or equal to Q, then what we get is a linearization. So we want to write well-formed formulas that say that this thing is a linearization of that, and then show that there exists a variable assignment that satisfies all those formulas, and therefore there's going to be, that's a proof that there exists a linearization of this. Okay, so let's write down a set of well-formed sentences in sentential logic which are going to satisfy what we want, which is that if you have a truth assignment that satisfies all the sentences, then you are a linearization of less than or equal. So how are we going to do that? So first, we need to say that the relation is transitive, okay? So this is what these well-formed sentences say. That if P is less than Q and Q is less than R, then P is less than R, right? So that's what transitivity says. So that well-formed sentence right there, using those three variables, that's what it says. And we want to add a well-formed sentences like that one for each triple P, Q, and R in our domain, okay? So we have actually a lot of sentences like this, one for each triple, and for each triple we have the transitivity. Then we need to add reflexivity, which says that for every P, we have that P is less than or equal to P, right? So this is a well-formed formula that consists only of one symbol, only one variable symbol, and we have one of these for each P that belongs to the domain, right? So for each P in the domain, one formula that says P is less than or equal to P. What else do we need? Antisymmetric, which says that if P and Q are different, then you cannot have P less than Q and Q less than P, right? So for different ones, you cannot have P less than Q and Q less than P. So these three already give you a partial ordering, right? So if you have something that satisfies all these sentences, we're already defining a partial ordering, but we want to get a linear ordering. So we add these new axioms that says that whenever you have P and Q in V, you must have that either P is less than or equal to Q or Q is less than or equal to P, right? So that's the linear ordering. Whenever you have two, you have to relate one way. And last, we need to say that the ordering we're defining is compatible with P. So if you had a relation in P, we have to preserve it in here. So this is what this one says. If whenever you have P less than or equal to Q in our partial ordering P that we had before, then you put the well-formed sentence which contains only one variable that says that P is less than or equal to Q. Okay? So actually, this one up here is already included in that one because whenever you have PP, like the same element, this one belongs to P. So we can erase that one and move the rest up. Okay, so what we have now is a set of sentences which satisfies the following. So if V is a true assignment that assigns to each variable symbol a T or an F, which satisfies gamma, so it's a true assignment that makes true all the sentences in gamma. So all the sentences, so suppose that's what we have. We have a way of assigning true and false to each variable APQ in a way that it satisfies all these sentences, and define that P is triangle-less Q if and only if the variable APQ is assigned true, then this triangle-less relation we just defined is a linearization of triangle-less. Okay, so what's left to show is that such a truth assignment exists. Okay, so what we need to show essentially is that this gamma is satisfiable, that there is some truth assignment that makes all of the sentences in gamma true. So we need to show that it's satisfiable, so that means we need to show it has a truth assignment, and here's where compactness comes in. So let's remember what compactness says. Compactness says that if every finite subset of a set of well-formed sentences is satisfiable, then the whole thing is satisfiable. right? So in this case, we do have an infinite set. Our set is gamma, and we're going to show it's satisfiable, but compactness says it's enough to show that every finite set is satisfiable, okay? So that's what we're going to do. Okay, by compactness is enough to show that every finite subset of gamma is satisfiable, so let's take one. And let's show that this one is satisfiable. Remember that we can use that, our theorem that we can use is that every finite partial ordering has a linearization, right? That's the assumption that we're going to use. And this is where this comes in, because now we have a finite set. So how are we going to use that? So let's consider the set of elements, the subset of V of the domain of all the P's that show up in gamma 0. Okay, so it's all the P's that they show up in gamma 0, and by show up, it means some variable. The variable could be of the form APQ or AQP essentially. So P could show up in the first part or in the second part, but whenever you have a variable, it refers to some P and to some Q. So take all the P's that all the variables in gamma 0 refer to. Note that this is a finite set of well-formed sentences, so it mentions only finitely many variables, so it mentions only finitely many P's, okay? And now we have essentially a finite partial ordering, right? And if it's a finite partial ordering, by our assumption, it must have a linearization that we can call, let's call it triangle less sub 0. Okay? So if triangle less than 0 is a linearization of this on V0, then if we define a new truth assignment that assigns APQ true if and only if P triangle less than 0 Q for all P comma Q that belong to V0. So we only consider now the points that belong to this partial ordering V0, and only for the variables that use those points. This is a finite partial ordering. It's a finite subset of this guy. So here there are only finitely many P's and Q's. So we're considering only finitely many variables, P's and Q's. So only for those we have a linearization, and we use the linearization to define a truth assignment. And we know that if you have a linearization, essentially you satisfy all the formulas in gamma, right? Because the linearization is to satisfy transitivity, that it antisymmetric, there is a linearization, and it extends P, right? So this one, we only need to do it for the ones in this subset. So we only care about the ones that appear in this finite set. So this is true. So it satisfies this subset gamma 0, because gamma 0 only mentions the things, the P's and Q's in there in V0. And for those, we have a linearization, because that's what we're using. That in the finite case, we know how to linearize spatial orderings. So in the finite case, we can make this gamma 0 satisfiable. Okay? So gamma 0 is satisfiable, and that's exactly what we needed. We needed to show that every finite subset of gamma is satisfiable, so we picked a finite subset and we figured a way of satisfying it. And to satisfy it, we had to linearize the partial ordering that mentions only the P's and the Q's that show up there. Okay? And now compactness tells us that everything is satisfiable. So all of gamma, now all gamma uses all the P's and the Q's from all the partial ordering P, and now that one is satisfiable, so that means there's a truth assignment for that one, that makes it true. And once we have a truth assignment for that one, we now define the linearization that we want from all the guys, right? So essentially what we're doing is saying, well, since we have this partial ordering P, every finite sub-partial ordering is linearizable by this theorem. And in principle, it's hard to put them all together. No, maybe we have like continuing many of these guys, and each of them is linearizable, but maybe different linearizations. And then how do we match them, making compatible? Well, compactness tells us that there is a way of linearizing the whole thing so that it's compatible with the whole partial ordering. Yeah. So that's the application of of compactness that we get. We went from knowing something is true for all finite partial orderings to knowing something is true for all partial orderings by an application of compactness. See you next.